right. Welcome to whoever may be listening. So let's have a look and review where we have been. Let me just check the view here. Yeah, so often the default Adobe is just to not have continuous scrolling. It's so annoying. Let us see. Okay, so when it comes to growth and decay problems and basic differential equations, let's have a little recap. So we have basic, growth, and decay problems. Now, if you followed the Math 108 Calculus for Life Sciences lectures, then we've done some of it. And I really have 5 different kinds of problems that I can use as part of my introduction. Let me just check the chat here. The very first one is the most basic I can come up with. Let's call it basic exponential growth. And let's come back to this page as we go further in this list. So for the basic exponential growth, we have that so let's pick a population here. Let's pick Y as the population size. So let Y represent the population size at time t. Then the information that scientists have found and that we're going to be given in a question is that the rate of change of this population is proportional to the actual population size at that time. This sentence then translates to our differential equation. The rate of change is some constant times the actual population size y, and I have some initial population size to start with. So we have this differential equation with k being positive, and k is called the growth constant. So I have exponential growth that if we solve this, let's take an example. Let's suppose k is 0.02 and my initial population size is maybe 100 individuals. Could be bacteria, could be individuals, could be people, could be fruit flies, could be anything that is growing. So if I use this example, then my differential equation is dy dt 0.02 y, and my initial population size is, for example, 100. Now solving this differential equation, we'll see for parts 1 and 2, they are very similar, and for all of them, they are very similar. I separate the variables because it's a separable differential equation, which of course I have to understand first, and then I integrate both sides to get the natural log of y equals 0.02t plus my integration constant. Then I solve for y because I need the function to be able to answer questions that the word problem might give me. And that's going to be e to the 0.02t plus c. I don't love the integration constant over here, so I'm going to put e to the c at the front, and then e to the 0.02t, and I'm going to call it m, or something else for convenience. That is just another version of my integration constant. Then I can use the fact that at time 0, I have 100 individuals. So when y is 0, time t is, sorry, when y is 100, time t is 0. And so e to the 0 is 1, and that leads me to this integration constant being 100, which is the same as my initial population size. So my function, which is the solution to the differential equation, is y as a function of time, initial population size, e to the 0.02 growth constant times t. And then I can use that function to ask questions such as, given a certain time, what is the population size at that time? Given a certain population, what is the time when I get that population size? And a variety of other questions. But they all come from that function, which in turn comes from the differential equation, which in turn comes from the fact that the growth rate is proportional to the population size at that time. And we've done some a variety of problems on that kind of basic population growth. If I were to graph this function, it would be, because time is positive or 0, I would have the sort of the high side of my exponential function with the y-intercept being the initial population size, and then it grows exponentially, which is why it's called the exponential growth. Now for the second one, we have, I'll call it radioactive decay, though it could work for other kind of decay questions as well, but mainly radioactive decay, where we have a very similar situation except that now my function name, my function variable y is going to represent the amount of the radioactive material left at time t. So it's a situation of I have some substance, some material, something that decays over time, that becomes less, and I'm trying to keep track of how much I have left at that time. But still I have the rate of change, which will now be a decrease, of course, is still proportional to the amount left over at that time. And this leads me to the same differential equation because the rate of change, whether it's going up or down, is still dy dt, proportionality constant times y, and this is now going to be a negative number called the decay constant. But it's the same looking situation, and I also have my initial amount usually known. So it looks exactly the same as up here, exactly the same. The only difference is that the k is now negative, and that's not going to have any effect on how I approach the differential equation. Let's take an example. Let's suppose I have a decay constant of negative 0.02, let's say again. And let's suppose I have an initial amount of 100. Could be 100 grams of the radioactive material or whatever. Then there's literally no change in how I approach this. But let's go through that again. I'm going to move the y to the left and the constant I keep on the right for convenience, integrate both sides. It's a separable equation, so I go about my business in exactly the same way. So then I have the natural log of y on the left and the constant times t on the right. Of course, integration constants, that's grouping the two indefinite integrals. Same as before, I'll spare you the details. It's going to result in a function that has my initial amount. I wouldn't call it the initial population size. In decay problems, we don't talk about a population. A population is something that grows. Some amount could change and decrease though. And e to the negative 0.02 t. So my function is still an exponential function, but now because of this negative in front of my independent variable, I know that the basic exponential graph, which of course continues on the left, is now going to be reflected in the y-axis. So if I were to graph this, I would start with some initial amount, and it would be the other side. Whoopsie, let me flatten that out a little. It would be the other side of the exponential function's graph, having a horizontal asymptote at the horizontal axis at y equals 0, meaning a radioactive material decreases down to something very small, but it never fully goes away. And then, especially in the radioactive decay section, this second type of problem, we have the concept of half-life. So for me to go from 100 down to 50 is going to take some length of time. I'll call it tau. And we'll call that the half-life. So this tau is the amount of time it takes for me to get a half of my original amount, which means that if I go into my function up there, plug in tau, I don't necessarily know what I start with. I could start with 100. I could start with any amount. E to the, let's stick to this. Now tau. Let's stick to an example for k, just to keep track of where it goes. and it's a 1/2 y0. I wanted to show a y0 because you see you can divide on both sides by y0, and it actually doesn't matter if I started with 100 or I started with 1,000 or very little. It doesn't matter. It's completely independent. So I now solve for tau, and I get negative 0.02 tau equals natural log of a half. So tau is natural log of a half over the decay constant. So in general, it would be the half would still be there because of this half life concept, and it would be a k. So this is independent of my initial amount. It's a key property of how fast this substance decays over time. Now in this case, we could perhaps calculate that in our example as log of 1/2 over negative 0.02. Let's just do that to get a number and see what that is. And we get 34.66. Now I don't know what it is. It could be years, it could be months, who knows. So this one is, in this example, 34.66. Let's say years. The radioactive substance takes 34.5 years to have its original amount. What's interesting about radioactive decay and this kind of curve, this exponential curve, is that if I want to go from here, I have 50. If I want to go down to half of that, it'll take exactly the same half-life time window. And if I want to go down and have that, it will take exactly the same half-life window. So I lose less and less and less because it's more of a proportional decay than a fixed amount. Every half-life window, I lose half of what I started with in that window. And you can see that I'm never going to get to 0. I'm only going to lose half to 12.5 and then half of that and half of that, and I'll never actually get an answer of 0. So the half-life concept is a key concept in the radioactive decay kind of problems that I list as number 2. All right. So I also have a bunch of questions on that we have done. So we have some population growth questions. I like the one that's a spread of a rumor that you can also model like this, not actual individual living things growing. And then we have eventually our radioactive decay questions. Sometimes half-life, sometimes radioactive substance. Carbon dating is a classic example where I use this kind of exponential decay, and so on. Let's get to the end of the section. Where is it? There we go. So another kind of question. Actually, I don't want to do this one as number 3. I'm looking for a question like this. Now, before I look at a specific example, let's just see what are the pros and cons for number 1, our basic exponential growth. Well, I'll say a pro is that it is easy. Easy to work with, easy to understand, easy to solve the differential equation is just easy. But now, if we actually do an experiment with, let's say, fruit flies in a jar. So I have my jar here. Could be an actual glass jar, which it was originally, I suppose. And I put an apple slice in there and a couple of fruit flies. And then I, of course, close the lid, give them some oxygen, see what happens. When we track periodically their numbers, we get something that is extremely close, near perfect on this graph. However, up to a point, when the space becomes an issue and they're really crammed in there too much, that it's going to slow this curve down. So there's a cap here somewhere due to practical space limitations, where after that kicks in, this graph isn't going to be an accurate model to describe how the population grows. So a con could be that it ignores any space limitations. So we could then say, okay, what if we change this model a little bit, trying to incorporate the idea that limited space does slow down the growth of the population. So we have here uh, growth with capacity, let's say. I have some space capacity. And honestly, let's just do it by example. So let's look at this number 1438 I have here. Example 1438. Mountain goats at a certain nature reserve, it can support no more than 4,000 mountain goats. Assume that the rate of growth is proportional to how close the population is to this maximum, with the growth rate of 20%. So if I just convert that to a decimal, it gives me my growth constant in a simple form. So 0.2 for our growth constant. And we have a starting number of goats, our initial population size. So now you see the wording is a little different. There is a proportionality concept, but it's not the growth rate isn't proportional to how much there is or how many there is in my population. It's proportional to how close the population is to this maximum. So what is the difference? First of all, let's call y the population size, the number of goats, population size at time t, and t in this case is going to be in years. It is important to take note, what is my unit for time especially? My unit for the function variable is obvious, number of goats. So let's have a look. Now I have the rate of change. It's proportional to something. Not proportional to y itself, but proportional to the gap between the population and the maximum capacity. So it's going to be proportional to the difference of the two, the capacity, which is 4,000, they say, and the actual population, where this guy is given, the growth constant is given as 0.2. So I should have just put that in. Let us do that to not make it any more complicated. And we can do a general one, I think, after this example. All right. So now let's see, is it more difficult to solve this differential equation? Well, yes, technically. How much more difficult? Can we still handle it? And what is the result? How does that end function look? Does it capture this capacity issue? So I separate the variables. I can only do that by multiplication and division. So I have to take the whole bracket to the left. So 1 over 4,000 minus y dy equals zero point 0.2 dt. Oh, I had my initial population, right? I had 1,000 mountain goats to start. That comes in later, of course. Integrate both sides. Now the right side here is going to be super easy, and I'll group the constants for the integration constant together now before I forget. The left side, what is the left side now? Well, that is a function of a function, to be fair, but is it a super complicated one? Is it one where I really need a full substitution? You're welcome to do a substitution, but I argue that it's not that bad. We can guess and check our way through this basic one. As if, let me give a guess. Let me try a natural log of the denominator. Then if I take the derivative of this, it's log of something, so it's 1 over the something. Yep, that's perfect. That's what I get in my target. Times the derivative of that inside something, which is -1, which I don't see, so I need to catch that negative when it comes out by the chain rule. And because the second part of the chain rule is so simple, you're welcome to do a full substitution, but it's overkill here a little bit. All right, now, because I'm doing this from a word problem, I want to answer questions, I need my function. So I need to, even though this is a perfectly fine general solution, I need to go further because I have a reason to. So let's take that negative over first. This is only one way of doing it. It's not the only way. To negative 0.2 t minus c. And then solving for this bracket will be rewriting the log equation will be the bracket equals e to the negative 0.2 t minus c. Let's shift up a little bit. So solving for y, I move y to the right, the e portion to the left. I get y equals 4,000 minus e to the negative 0.2 t minus c. Now I'm going to do the same kind of integration constant adjustment that I did for our basic exponential growth because I don't love the integration constant in an exponent. It's going to be a lot nicer if I put it out in front. And then, of course, m, if anyone cares, is going to be e to the negative c. It doesn't really matter. It's a constant that I need to resolve. Now I need to use the fact that at the beginning I have 1,000 mountain goats. I can use that now. Plug in 1,000 for y. Plug in 0 for t. And I see that this, of course, equals 1. So that means m is 3,000. So I have my function. My function describing the growth of these mountain goats is 4,000 minus 3,000 e to the negative 0.2 t. Let's put a box around that. Now, what does this graph look like? before I continue answering questions, does this function make sense in terms of what the model is trying to do? Incorporate that capacity. Well, if I see how much space I have here. Let's make a new page because this isn't easy for everyone. If I go back to my transformations of basic exponential functions, and I just take something simpler, let's remember, if I wanted to graph y equals, let's say, 4 minus e to the, I want to make it look similar to this, right? So I need a negative in front there. E to the negative x. That's a simple, while still capturing the essence. Well, I was going to graph basic exponential function. We're just doing a very rough one. Then I'm going to chain that with, well, you have some options which one to do first. I mean, I can rewrite this to negative e to the negative x plus 4. I like to, it doesn't really matter which negative you take care of first. Like, let's do the outside one. Negative outside e to the x. What is that going to do to my graph? That is going to flip it in the x-axis. The y values now become negative. So if I do that, I'm going to get something down here. Then if I chain that with replacing x with a negative x, what is going to happen to the graph? The previous graph is going to be reflected in the y-axis. So it's going to, whoopsie, let me not touch the x-axis. It's going to look like this, more or less. And lastly, I'll go over here. I want to add 4 to that. And that is going to shift the graph up by 4 units. Now remember, this y-intercept was 1, so this y-intercept is -1, so this y-intercept is still -1. So when I shift it up, it's going to go up here to 3. The x-axis, which was at y equal to 0, was a horizontal asymptote. It's still a horizontal asymptote in the second one. It's still a horizontal asymptote in the third one. When I shift it up, that horizontal asymptote is now going to sit at 4. It's going to shift up and sit at 4. And that's the situation I have here. So my number that I'm adding is going to be where the horizontal asymptote sits. With my couple of negatives, I'm going to have sort of a backwards up growth of my exponential function towards that asymptote. So we're going to get the following graph. Time, of course. I'm going to have a horizontal asymptote at 4,000. And I'm going to start at 1,000, my initial amount, initial population. Oh, come on, not straight. Have it nice and bendy at least. And it's going to taper off as I'm getting closer and closer to that capacity, but it's still a section of the exponential graph, the exponential function. So I have this capacity that it can't cross this 4,000 line. It's going to get stuck. There's a maximum capacity that the area can hold. So the model is using exponential growth, but at the same time having built in that capacity. So it's one step forward, a little bit more general. Is it perfectly general? No, of course not. But we're trying to keep things simple while still inching forward in our practical generality. So we can answer some questions, I suppose. Solve the general limited growth differential equation. We did that. Write the function. We did that. What will the goat population be in 5 years? That's easy enough to answer. In 5 years, we simply use our function with 5 as the time variable, value, 4,000 minus 3,000, e to the negative, what was it? 0.2 times 5, and we get an answer. Let's see what that answer is. So after 5 years, I get 2896.36. So we'll get approximately 2,896 goats. It makes sense because they're goats that we round to the nearest integer. We can't get a third of a goat, then walk around. Now we can add to this question. Instead of doing brand new questions, we could just add some more questions here. When will we have, let's say, 2,000 goats? Then I want to solve for my time value when the y value target is 2000. So I simply set y of t equal to 2000. So that means e to the negative 0.2 t. Feel free to break it up into more steps and pause and think about it if you're watching this after the fact. I want to move this to the right, 2000 to the left to get 2000 over 3000. I'm just running out of space here a little bit. So then I get negative 0.2 t equals log of 2/3. So t equals log of 2/3 over negative 0.2. Let's see what that is. And we get 2.03. So when will we get that? At approximately the 2-year mark. We will have 2,000 goats. And then it slowly, it still grows, but slower and slower and slower, the closer it gets to that capacity, the smaller the difference between the capacity and how many goats there are, and the growth rate is proportional to that. So if the difference gets smaller, the growth rate gets smaller and they naturally slow down. Now, in truth, what would be more realistic is, let's say here, more realistic is a combination of 1 and 3, where we want to have the following picture. we want to have the following idea. I want to start with my initial amount. I want it to grow really fast, exponential, because initially there is no space limitation and awareness at all, because there are so few initially. So let me just make a smoother line here. There we go. So initially, come on, there we go. It should resemble very closely the basic exponential growth. But then I do have space limitation issues. So at some point, I also want the capacity model to kick in and have the growth curve slow down towards that capacity. So a combination of these two seems to be the most realistic I can get right now. But unfortunately, we can't jump to that right now because it is much more complicated. I want to run through some more basic ones, and then perhaps we are more ready to see what does this differential equation look like. And because, to be honest, the more realistic I want to get, the more complicated the math is going to be. So it's a fine balance between the two. I want to capture the essence, the most important things of the practical problem, but I don't want the mathematical side of things to be a complete nightmare. Where is the balance? And this is called the logistic growth model. It does have a much more complicated differential equation that we should build up to and leave until the very end of our discussion. So next time we will look at number 4 and number 5, other variations of growth and decay with still the same level of differential equation, eventually working our way up to something very realistic. All right.